All right, welcome to the lecture, Deep Learning for Natural Language Processing, summer semester 2020. In this lecture today, we will be talking about word embeddings part 3, and in particular, we will talk about how to embed complete sentences rather than just individual words as we have seen in the previous lectures. Um, Good, so let's go into the lecture. So we start out with how do we embed larger units than just individual words, namely sentences or maybe whole documents. So our method so far only embedded words in a low-dimensional dense space. How about larger objects such as phrases, sentences, or whole documents? It would be really cool if we could represent the meaning of a sentence in a low-dimensional space. And why would that be the case? What could we use a sentence embedding for? So one thing that we could use it for is clustering. Let's assume you have your documents up here, and you want to find out which of these documents talk about politics, which ones talk about sports. So you want to group them into different clusters, and we have seen in lecture 2 that there are like unsupervised clustering algorithms such as k-means or k-means that could do something like this, and but they need a representation. They need a vector representations of the objects that they are clustering, and we could use a word embedding sentence embedding technique, or we could use a document embedding technique if we had one to get such representations. And if we only have a sentence embedding technique, well, what we could do is we could embed every sentence and then take the average in order to get a vector representation of an object that comprises multiple sentences. Another application scenario is retrieval. Imagine you want to find something, and this something could be an answer to a question, or a similar sentence to a given sentence, or a translated sentence to an input sentence, right? And each of these cases, we could again embed the question as a vector, and all possible answers could also be embedded as vectors. And then we could, for example, find for the answer that has the lowest or the highest cosine similarity to the question. And equivalently for these other cases here, in this latter case where we want to get the translation, here we would have to work in a cross-lingual space, right? Because otherwise it would not work to get translations um, for an input sentence. And beyond like clustering and retrieval, we can also do that for classification. So the intuition is here that if we have a text classification problem that involves sentences, and there are a couple of these classification problems, then we could and what are these problems? For example, so one problem could be to classify whether a sentence is positive or negative. Another one could be to classify whether a sentence is argumentative or whether it's non-argumentative. So there are a couple of such classification problems in NLP that have become popular in the last couple of years. And we could then, if we have, and they naturally classify sentences in several classes, so we could directly represent the sentence as a vector and then do the classification. And of course, we could, as an alternative, we could also use word-based models like the ones we're going to see and that you've already very briefly seen in the introductory lecture, where, for example, we talked about for example, about convolutional neural networks, CNNs here, or also recurrent neural networks. So we could also use such a model. And these models, like CNNs, they also induce sentence representation. So they start out from words, and then they go up to the level that then they build a representation for the whole sentence, and RNNs do the same. And then from this representation, they do a classification. And then the idea or the argumentation is when the training data is very small, then it is very difficult to get good sentence, or then it might be very difficult to get sentence representation just from the given training data. And maybe these sentence representations can be learned unsupervisedly on huge corpora. Therefore, these sentence representations may work better than representations learned from small word level models. So how could we embed sentences? So here we sketch two, like, which I called naive approaches. First one is we treat each sentence as a long word. So we take the sentence, take the word in the sentences, we patch them by an underscore. Now this is a very long word, and then we treat each such long word exactly like in the case of in the word-based case of the SIBO and skipgram model. So we would predict the neighbors, or from the neighbors we would predict the middle word, and the word is now a patched sentence. So we would just go into a corpus, have a sequences of such sentences which are treated, each of them is treated as a word, and then we predict the context, right? What's the problem with this? The problem, of course, is that we would have extreme data sparsity, because it would be very unlikely to see the same sentence twice, because there are so many possibilities how to create sentences, and it would also be very unlikely to see the same context a couple of times, right? So each sentence would actually be unique, or almost unique. I mean, there would be a high chance that a sentence is unique, and this leads to extreme data sparsity, and that's why the problem would probably not work well. Naive approach number two is what I've already said for the document embeddings. When I said we take the average over all the sentence embeddings, we can do the same for a sentence embedding. We can take the mean embedding of each of the words. So we have all the words, we have our word embeddings, we take the arithmetic mean, so it's just like the standard average. We take you add all the embeddings up and divide by the number of embeddings that you've added up. And so the embedding of cat set on a mat would be the average over all these 1, 2, 3, 4, 5 words. So what is the problem with that? The problem is it is known by laws of linguistics that half of all the words in a sentence are function words, and these function words are like articles, the, a, the, and a. Like this is a function word. Maybe this is also prepositions are also function words, and they should really not contribute a lot. But if we do this naive averaging, then they contribute just as much as all of the other words, and this is maybe not a good thing, right? What we could do to address this is we could discard high frequency words. For example, if we use a stop word list, or we determine the high frequency words from a big corpus, so we could like downweight them or remove them. That would be an option. However, the second fundamental problem is that this averaging is totally word order insensitive. So the embedding of cat set on a mat and mat cat set on there would be totally the same, which of course is is not a good thing, like, right? So that's probably not an ideal representation that has this property of word order freeness. However, still the mean word vector, so the average word embedding, is still a reasonable baseline for sentence embeddings that is often reported. So now let's talk about more sophisticated approaches. To talk about these approaches, we need to briefly look ahead. And we have to introduce encoder-decoder models, because these models are very popular for inducing, or they have been very popular for inducing sentence embeddings, or sentence encoders as they are nowadays called also. And to understand encoder-decoder models, we would have to look at recurrent neural networks, which we will see in lecture 8 again, and we will see encoder-decoder models in lecture 9. So we're going to introduce RNNs, even though you have already briefly seen them a couple of times in this course already. So we motivate RNNs again. So how do we motivate them? So we motivate them by the task of part-of-speech tagging. And part-of-speech tagging is we want to label each token in a sentence with its part of speech, and the part of speech is the word class. And the word class is something like noun, verb, adjective, etc. So so imagine you have the sentence "I can see the cat." So we would like to label all of those words. Like I is the pronoun, can is the verb, or the modal verb maybe. See is also verb. There is article, cat is noun. So that's the labels we want to get. But now let's say we are here at the word can. So if we want to make an architecture, we would feed can, of course not can. We take its vector, its vector representation. We feed it into a network. We have a softmax here and get some classification out. That's a possibility. Of course, it's better to include context, right? Why shall we include context? Because we shall include context because that helps to disambiguate, right? Because can could either be a verb or it could be a noun, but if we have this context here, then that can help disambiguate. So if we include more context, then quite likely we are better equipped with solving this problem. However, the question is, how much context do we want to add? We cannot simply add more and more context, because we would have many more parameters. Then depending on the amount of data we have, that could lead to overfitting, and also the speed would go down, right? So just increasing the context of this network could lead to problems, and we also don't know how much we have to increase. Yeah, what is the ideal context to take into consideration? So we would like to have a different architecture that has the following properties. It has an infinite context window, but it does not have too many parameters, and it makes a prediction at each time step, right? Because this is exactly the property of part of speech tagging, right? Or a task like part of speech tagging, sequence tagging task, where you have to make a prediction at each time step. So in this model is the recurrent neural network that you can see graphed out here. At each time step, so we have the time steps here, we make a prediction. We have this recurrent connection between the hidden states. So these are the hidden states. We have a recurrent connection. And this hidden connection is the reason why we have infinite context. How can we see that? If we are here at this position, can we then take all of the other words into account? Yes, we can take all of the other words into account, because this hidden state is informed by this hidden state. This hidden state is informed by can. It's also informed by this previous hidden state, which is informed by I. So we really see all of the left context. No matter where we are in the sequence, we always have all of the left context given. And note that somewhat unfortunately in this figure it's called, the output is called H, while we would usually write Y. And how do we get a model that's not using too many parameters? Well, by doing parameter sharing, right? So these parameters, so here are the matrices U, V, and U, W, and V, and you see that they are the same everywhere, right? So we really have parameter sharing. And we can condense that into an equivalent notation by making this like MLP kind of architecture with a with a self-feeding loop, right? And the math is also not very difficult. Like you have the input xt comes in, is multiplied by the matrix. To this we add st minus 1 multiplied by this shared matrix w. Of course, we have our bias values, and then we apply nonlinearity, and this in total gives us the hidden state vector at time step t, and then from this hidden state vector we do our standard like feed forward layer to get the output, and usually the output activation function would be the softmax in natural language processing at least. So the benefits are we have infinite influence from the past, at least in theory. We will see in lecture 8 that in practice this is not always true. So in practice these models are more difficult to handle, but at least in theory you have infinite left context. We could also, for some tasks, we could make this bidirectional. Then we also have infinite influence from the future. And we have fewer parameters because we have parameter sharing. And we have these small matrices U, V, and W. And now let's make an example. We have the input erastican. Let's say we have our embeddings for our 3 words, x1, x2, x3. These are embeddings. Let's say the true labels are determiner, adjective, noun. And let's say they're encoded as one-hot vectors in a 4D label space. What does it mean? It means that we have 4 possible labels, right? So don't confuse that. We only have 3 words. Coincidentally, all 3 of them are represented by 3-dimensional vectors. So this would, of course, not generally be true. These vectors would be 100-dimensional, for example, in reality. But now we encode them by 3-dimensional vectors, and we have 4 possible labels. So we have a 4-dimensional label space, let's say. And the activations are ReLU for the hidden layer and softmax for the output layer. Let's say these are our initial guesses for the matrices U, V, U, W, V, and the bias values are 0, and this H0, so that's the hidden state at time step 0. We set that to 0, right? We always have to always have to initialize the initial hidden state. And here are the matrices. And why do they have these forms? Because U is like U is the matrix that is here at the bottom, so the input is 3-dimensional. So U has also to be 3-dimensional here, and then it has to have the same dimensionality as the hidden layer. The hidden layer is 2-dimensional, so that's 2 by 2. And then the output we said that should be 4-dimensional because we have 4 labels, so it's 2 by 4. So what's coming in? That's our input. Then we compute the hidden layer at time step 1. How do we do that? We multiply this vector by U, so that's just a vector matrix multiplication. Then we add H0, that's 0, so that gets cancelled out. B is also 0, so we get H1, which is 1, 1. This is ReLU, right? So we have 1, 1 here. Once we've computed that, we can compute the next one. The math is very straightforward. We take x2, which is this one, multiplied by u, that was given. Then we take h1 multiplied by the matrix w. We add b, which is 0 in our case, and we put the ReLU, so we get 5, 4 here. Here we get 3.57. Once we have computed all 3, so then we can also calculate the output layer. And of course the output layer is a probability distribution because we want to do a classification for each time step. And the truth vectors, let's say these are the truth vectors, right? Because this one says this is label number 1, this is label number 2, and that is label number 4. Good, now that we have seen RNNs, let's go to encoder-decoder models. So RNNs are MLPs with a feedback loop and a time delay. And what are RNNs? What are encoder-decoder models? These are 2 RNNs stacked together. They're a little bit modified. The first RNN has no output, so it's not making any predictions. But instead what it's doing is it's taking the input and it's encoding the input, and it is really representing the meaning of the input in the last hidden layer, so to speak. And then it's feeding that meaning into the second RNN, which has no inputs. But this is like a decoder model, so it's generating something. It takes a representation as input. From this representation generates the words, feeds the predicted word back into, so this would actually be fed back into the second hidden layer. From this second hidden layer, then another output is predicted. And we predict as long as we have not seen a special symbol that indicates the end of the prediction process. So and as I said, the last hidden layer, the value of the last hidden layer is fed into the first hidden layer of the second RNN. And the last hidden layer is the representation of the input, as I have said. And of course, the most popular application scenario of these models has been, in the last few years, have been machine translation, where you translate a German sentence into an English sentence, or any other language pair that you may come across. Okay,